There is one thing we forgot to talk about was the power in rotational systems. Well, we remember the power in translational system was F times V. So that was the power if we had something moving um, with a velocity V and there was a force which was being applied at that time when it was moving with a velocity V. Okay, so that was the case when we were talking about translation, which means the movement in straight line or movement or just movement. And when we have to talk about power in angular systems, we see that we can certainly draw an analogy because we can certainly draw analogies in all the equations between translational and rotational system. So F simply gets replaced by T and V simply gets replaced by omega. So this is the power for rotational systems. So for example, let's say, let's take an example, a quick example. If some object looks like a face and about this axis, let's say this is some axis Z which is going into the plane or out of the plane. Okay, about this axis, let's say I is being given to be 2 kilogram meter square, and the torque which is being applied, let's say, is being given 4 Newton meter. So what is going to be the power? So there's something that is moving it, that has provided a torque of this amount, and that is moving the whole thing. So there's something, some machine running this, or twisting or turning or rotating this whole thing. There's a machine. So how much power that machine is providing to achieve these parameters? So what is the power after, or you can say what is the power supplied by machine after time 4 seconds? Okay, and let's say that it initially started with initial velocity, initial angular velocity 0. So let's see, well, all you have to do is calculate these two parameters. Tau we already know, all we have to do is calculate omega. So what is going to be the omega after time 4 seconds? We know that omega is omega I plus alpha t. Omega is 0, alpha will be nothing but 4 over 2 multiplied by 4, that gives us 8 radians per second, and that's why we get power to be 4 times 8 radians per second. That is nothing but 32 watts, right? So that was a simple example. But the main reason for this lecture was to discuss equilibrium. So what is equilibrium? Let's take an example. Let's say we have this rod here, and this is hinged here so it can move up and down, and this is the wall. So if you let this go, this guy is going to go down. But if you hinge it with a wire, this is going to stay in its place. So what is that something which you can tell about this system, which tells that this system is in equilibrium, which means it's neither going up nor going down, or it's not really moving at all? What can you really tell? Well, you can tell that sum of all the forces is 0 on this system. Also, you can tell the sum of all the torques is 0. Both the conditions should be met. For example, let's say you have this thing which is hinged here. You apply a force like this and you apply a force like that. But is this guy in equilibrium? Well, no. The net force is certainly 0, but net torque is not equal to 0. In fact, the whole thing will be moving like this, right? So the whole thing will be moving like that. And also, let's take another example. Let's say you have a free stick, and you apply a force F here and you apply a force F here, you can certainly tell that net torque is zero. But you really cannot say the same thing for the force. In fact, this whole thing will be moving forward. So all you need is that the net force as well as net torque both should be zero to achieve equilibrium. And we'll solve some problems